Hello and welcome to a new Voltlog. Today we'll be taking a look at this mini DC power supply I found on eBay. It is available from eBay and AliExpress as well. Banggood doesn't seem to list this one yet, but I will add links in the description if you're interested in getting one. I guess the whole point of this power supply is to have a DC input of 24 volts with an adjustable output voltage capable of up to 2 amps and a second rail which is fixed 5 volts 2 amps. The cost is around $11 with free shipping depending on where you order it from, which is not bad if it will deliver all its advertised feature. At the same time, you get voltage and current measurements on this tiny LCD screen which is present on the front panel. And interestingly enough, they designed this retail type of box for the product like it was supposed to be sold in stores, so you don't see this often. But here is the typo that I noticed. It uses new low voltage and high currency efficient DC to DC power technologies. That should be interesting. And it seems to be manufactured by the Shenzhen Deek Technology Company. Yeah, it's somewhere in Shenzhen, China. So let's take the unit out of the box. And it feels quite light, but the plastic seems okay in terms of quality. It feels similar to the ABS project boxes that you can buy for various DIY projects. The size is 80 by 80 by 25 millimeters, and the weight, according to something I read on the box, is 85 grams. So in the box you also get a short pair of cables with some alligator clips and a 2.1 millimeter barrel jack. Guess you're supposed to build yourself an input power cable for the power supply using these. On this side you get the main input, so it's a 2.1 millimeter barrel jack, and you also have the power tactile switch. On the right side you have the voltage adjustment, which seems to be composed of two potentiometers, one for coarse and one for fine adjustment. We'll see later how that works out. And on this side we have all our output connections. So this is the 5 volt 2 amp rail, which is independent and fixed. You get a USB type socket output and a pair of 0.1 inch header pins tied to the same rail. On the right side we get the adjustable rail with the main output through this screw connector, and they have a cutout on the back for the screws, so you can access those, and the same 0.1 inch header which is tied to the same rail. So I can see how they designed this to work with breadboards. You get your DuPont jumper leads and connect this power supply to your breadboard or your pin headers on your Arduino or Raspberry Pi very easily. So I guess now it's time to power it on. This is just a 12 volts power pack, but it will be okay for showing you how the interface looks like. Okay, so the LCD is on. Looks like we have voltage and current measurement for each of the rails, and they are correlated with the physical position of the rails. That's nice. And it seems that we have 100 millivolts and 10 milliamps resolution, judging by the position of the dot, which I guess it's okay for breadboard stuff jobs. It would have been nice to have 10 millivolts resolution as well, but we don't get that. Unfortunately, the silk screen is wrong for the adjustment ports. The coarse adjustment seems to be the fine adjustment, so they're the other way around. But that's not such a serious issue, just something that you need to be aware of. Now I would like to check the accuracy of this measurement showed on the onboard LCD. So I have a couple of multimeters on voltage range connected. So the one on the left is showing 5.00 volts. Fluke is measuring 5.04, close to 5.05. So about 50 millivolts error in measurements. The one on the left is showing 12.9 volts, and we're getting 12.9 volts on the multimeter, so it's slightly better, but you don't get that extra digit. So at 20 volts, yeah, it's okay for the second measurement. It might have different calibration constants for this second voltage divider. Yeah, so we're getting better results on this right hand measurement for the adjustable rail, but like I said, you don't get the extra digit here to be able to measure that difference. I know there is also a calibration procedure. You hold the power button while applying power, but that will do just a zero calibration, so I'm not sure how that is going to be useful. It will only help when the components inside change value over time. For checking the amps accuracy, we're starting with the 5V fixed rail, and the dummy load is right now set for 500 milliamps measured by this Fluke 87, and we're getting just 40 or 50 milliamps shown on the screen, so it's completely off. Let's go up to 1 amp. Yeah, it's showing 120 milliamps. It looks like it should be multiplied by 10. It just doesn't measure the amps correctly on the 5V rail. Let's go up to the full rated, which is it, 2 amps? Yeah, it's 2 amps. So it's showing 200 milliamps. Yeah, like I said, it should be multiplied by 10. Who knows, maybe they got something wrong in the software, or maybe I have a problematic unit here. They might have mixed up a resistor inside, which sets the gain or something like that. I'm not sure. Now for the adjustable rail, it seems that we're getting better results. We're even getting the 10 milliamps resolution. So as you can see, I'm increasing the dummy load in steps of 10 milliamps, and that is reflected on the measurement right here. And it seems to be spot on to what the Fluke is showing us. So let's go to 1 amp. Okay, we're getting pretty good results. Just a 4 milliamp difference from what the Fluke is measuring. This is 1.5 amp, and this is 2 amp. Let me check once again. The full output is 2 amps. Yeah, let's also check the voltage adjustment. Yeah, that works just as well. So I don't know what happened to the fixed 5V rail amps measurement, because that wasn't working at all when we checked it earlier. Next, we should take a look at the output voltage ripple with load or no load conditions. So for that, we're going to be using the trusty 60 watt load. By the way, if you're interested in one of these, there will also be a link to this in the description below. I have tested many dummy loads, and this one is the best out of the bunch. I also have my scope connected on the output of the fixed 5V rail. So now we can see that we have approximately 200 millivolts, 210 millivolts peak to peak voltage noise with no load on the 5V rail. Let's start the load with a 500 milliamp load. The noise increased to approximately 250 millivolts peak to peak. Let's go to 1 amp. At 1 amp, the noise increased to approximately 300 millivolts peak to peak, and it looks like it increased in frequency as well. Let's go up to 1.5 amp. And right now I need to adjust my scale on the scope. Okay, so at 1.5 amps we're seeing approximately 320 millivolts peak to peak. It varies, but it's around that value. Let's go up to the full rated 2 amps. Yeah, so it's around 360 millivolts peak to peak noise at the full rated 2 amps. Now let's also take a look at the voltage ripple on the adjustable rail. This is our base measurement. I have my bench LED lights turned off because if I turn them on, just look what happens to the noise. So as you can see, the bench lights do introduce some noise on the measurement, so it's important to take into consideration things like this and keep them off while you do the measurements. So our base measurement about 540 millivolts peak to peak with no load. Now let's turn the load on at 500 milliamps. So now with the load on at 500 milliamps, the peak to peak noise actually decreased. We are at 340 millivolts peak to peak. Let's increase to 1 amp and we're seeing about 400 millivolts peak to peak. Let's also go up to the full rated 2 amps and we're seeing about 410 millivolts peak to peak noise on the full rated 2 amps that this rail can output. So I would say those are pretty good results for an average DC to DC converter. You also have to consider the fact that we're not using the best measuring method here. I'm using the ground lead on the oscilloscope probe, which introduces a lot of inductance and picks up a lot of common noise from the environment, and it's not ideal to measure like this, but it's pretty difficult to measure otherwise, and it wouldn't be comparable between the two measurements. At least with this method I've used the same setup for both of the rails, so we can compare the results. And it's up to you to decide if that's acceptable for the kind of projects you're working on. Usually for breadboard stuff you can always add some decoupling capacitors close to the module or to the actual IC that you have plugged in into your breadboard, and you can filter out some of that noise even further. You can also do some local filtering at the point of entry on the breadboard on the power rails, which are usually on the sides of the breadboard, and that will also help. Next, we should also check if the power supply can output its full rated power for extended periods of time. So I have my dummy load set for 2 amps, and I'm going to leave this running for 15 minutes maybe, and then I'm going to come back and check the temperature of the unit. So the power supply has been running for the past 19 minutes or so. It's now close to 20 minutes. It's been outputting 12 volts and 2 amps. So it's right in the middle of the input power supply voltage, and it's barely hot. It's just warm, nothing to worry about. I think it will survive just well. That is to be expected from these DC to DC converters, which usually have an efficiency of around 90%. So not much heat to be dissipated inside this power supply. So it's been running for about 25 minutes on the fixed 5 volts rail at 2 amps, and same as before, it's barely warm. It's quite okay, so it can handle the full maximum load. No review would be complete without a teardown, so next we're going to take a look inside, and judging by these covers on the back, I suspect there are screws holding this thing together. So let's try to pop one of these. Yep, it looks like there are screws in there. So it looks like it comes apart fairly easy. It was only held in by those 4 screws. Look at the nice walls built around the pin headers. So Not sure what the purpose of this shield is. Maybe to keep everything together and prevent you from bending those pins inward and shorting between them. That might be a possibility. So we have quite a compact and clean construction here. Single PCB with everything mounted on this side except for the LCD, which is on the back side. Once again we see this name, Dick Robot, product ID 8128, and frankly it looks really clean and nice. You don't usually see this kind of clean construction in these Chinese products. So let's take a closer look at what we have on this PCB. On the upper side we got the power tactile switch, we got the DC input, we have a Voltlog HT16218. This, judging by the placement and all the tracks going to the LCD connector, this might be an LCD driver. Looks like this is our microcontroller. Let's try to read the numbers of this. So this is an STM8S microcontroller, which is quite common these days in new designs coming from China. We have a couple of LM358 op-amps from Texas Instruments. These are most certainly handling the current shunt measurements. By the way, the current shunts are right here. Looks like they've used 10 milliohm shunts. This chip right here looks like it's a DC to DC converter handling the fixed 5 volts rail. And this one right here, it's an XL Semi XL405E1, also DC to DC converter, which is handling the adjustable rail. We have a nice beefy Schottky diode. The inductors look like they could easily handle the rated 2 amps. And this right here looks like an input protection diode maybe, or it could also be, you can do reverse polarity protection by using a MOSFET and a Zener diode and a resistor on the input. It could also be that. I haven't checked this number, LR7843. So it could be a MOSFET or one of those dual Schottky diodes for protecting the input. On the back we have nice thick tracks with exposed copper with solder that has been added to that to increase the current carrying capability. It's always nice to find something like that in a product. It looks like someone was thinking when they designed this board. And like I was saying, maybe they mounted the wrong value resistor for the gain of one of these amps. So that's why on the fixed 5 volts rail we're getting results that look like they're divided by 10. But the system is still measuring, the ADC is getting values, they're just 10 times smaller than what it is expecting to see. So that's why I guess that could be an easy fix if one would like to investigate the issue. It could find the fault and replace it. Let's check the brand of the capacitors. These look like LQ. I'm not sure what brand of capacitors they are. They could be that Lilong brand. These smaller ones are Chengxing, and they're all marked as low ESR capacitors. But in the product that costs $10 and has an LCD, you really can't complain about the quality of the capacitors inside. But overall, let me tell you that the soldering looks really nice. Almost no flux residue. Just here on these two pins I see a bit of residue. Well, that's a capacitor. Maybe they hand soldered that one. They changed the value or they replaced it. maybe it was reworked if they found a problem. But overall, really clean construction. So now let me give you my final opinion on this gadget. It does have some disadvantages. The voltage ripple might be too high for some applications, but that can be fixed with some external bypass capacitors. I think there's even room to improve it internally. The current measurement for the fixed 5 volts rail is not functional, although I could be lucky to get one of these with a faulty measurement. You could be getting one that works just perfectly fine. And also the coarse and the fine seal screen on the enclosure were wrong in my case. They are reversed. Who knows, maybe I got some older revision and on the newer ones it's fixed already. But this kind of power supply also has its advantages. You get 2 rails, it's compact and convenient to use for small projects. It's portable, it can be powered from an external battery pack, and you got your adjustable power supply. It has good accuracy on the adjustable rail for both volts and amps measurement, and I'm sure it would have similar performance on the fixed rail if the circuit would work, and in my case, like we noticed, it does have a fault. So I guess a gadget like this is worth $10 because you could replace that linear breadboard power supply with a more efficient one which will give you voltage and current display as well as adjustable output, and you can take this anywhere with a battery pack and you have your power supply. As always, thank you for watching this video. If you found it interesting, don't forget to hit the like button and maybe subscribe to my channel, and I will see you next time. Just when I finish putting everything back together, I forgot to add this button for the power switch, so I need to take it apart once again and fit this small plastic piece. Stuff like this happens during teardowns. So everything is back together nicely right now, even the power button. But guess what? I forgot to take high resolution pictures of the PCB inside, and I need these pictures for the blog post on this power supply. So I guess I'm going to take it apart once again.